Module 6 is on trigonometry. Historically, this is one of the harder subjects in pre-calculus, and so this is really important now to review it so that you can approach more complicated problems in calculus that involve trigonometry and trigonometric functions. In this module, we will talk about everything starting from the basics of unit circle, angles and their measurements, defining all the important trigonometric functions, sketching their graphs, as well as doing trigonometry, talk about trigonometric identities and equations. So let's start from the beginning of what is a unit circle, how do we define angles, and what do we measure them in. A unit circle is a circle of radius 1. So this is just an important basic figure to start thinking in terms of angles about. Now, we make a convention of measuring angles from the positive x-axis counterclockwise. This is the rotation that will produce positive angles. It doesn't really matter, but it's important that we all have the exact same way we measure angles, so this is the convention that we take. Then the question comes of how to measure an angle, and we generally talk about two different measurements, radians and degrees. Radians come directly from the actual circle. 1 radian is a measure of an angle that is made when we take 1 radius and wrap it around the circle. So if I just take the length of 1 radius and I wrap it around the circumference of the circle, the angle that is formed by that is exactly 1 radian. Of course, I can take the radian and keep doing that. So my second radian would be somewhere here. My third radian would be somewhere here. And we notice that to get to the negative x-axis, I have taken 1, 2, 3 radians and just a little bit tiny more. So this should be a familiar measure of 3.14 and so on, which we call pi. And if I keep going around the circle, I will see that I have, so this is 4, 5, 6, and a little bit more. So this will be 6 and 2.8 and so on, or 2 pi. So pi is this important constant that we refer to. It does not have a finite representation. It is what we call transcendental. So we have given this constant a name pi to be able to refer to it easier. So this is when it comes to radians. Pi is going to be the negative x-axis, and then 2 pi is going to be a full rotation. When it comes to degrees, there are actually a number of different types of degrees. The most common one we use is for 360 degrees in a circle. And let's think about that for a second here. Where does this number come from? This doesn't come from a circle. There's nothing about the circle that screams 360 as the measurement. It means that we were going to split up a circle in 360 tiny little slices, each of 1 degree in width. So what is so special about 360 in terms of our lives? Trigonometry was first invented and studied by ancient Greeks who were really interested in the motions of the planets. So of course 360 is likely referring to the number of days in a year, which is 365. Now, 360 is much better because it's divisible by many things. So if we assign 360 to the full rotation, then each quadrant is going to be 90 degrees, and even dividing it even further will produce integer numbers as opposed to 365. So this is just where 360 comes from. It was a convenient measure that came from the real-life application. Engineers sometimes use 100-degree circle measurements. We're not really going to talk about those. So let's talk for a minute about how to label the circle and the measures of the angles in terms of radians and in terms of degrees. So we start off with the positive x-axis with 0, both 0 radians and 0 angles. Some of the nicest angles you guys probably remember from high school are 30 degrees, 45 degrees, and 60 degrees. So in terms of degrees, they are 30, 45, 60. In terms of radians, they will be pi by 6, pi by 4, and pi by 3. Okay, so this is 30, 45, and 60 degrees. Then we get to the vertical, or pi by 2, which is also 90 degrees. And then as we go around the circle, we have pi, which is 180 degrees, 3 pi by 2, which is 270, and the full rotation makes up 2 pi, or 360 degrees. It's actually fairly easy to count in pies if you count in fractions. So for example, I know that each quadrant is pi by 2. So this is 1 pi by 2, 2 pi by 2, 3 pi by 2, which is how I get my expression here, right? So same way, for example, if you were to count what is 5 pi by 4, you can count in pi by 4s, and we need 5 of them. Pi by 4 is a half of a quadrant, so this is going to be 1 pi by 4, 2 pi by 4, 3 pi by 4, 4 pi by 4, 5 pi by 4. So it's going to happen somewhere here. Okay, so keep in mind that there are some nice shortcuts to count in terms of slices. Now, once we have our angles, we might want to think about how things work around the circle. So again, studying, for example, motions of planets, we're going to think of, let's say, the center as the sun and an Earth rotating around a circular orbit around the sun. So the Earth is going to be this point that moves around the sun, and we, of course, are likely interested in its position at some point on the circle here. So if we fix a coordinate system the way that we did here by introducing x and y axes, I can connect the origin to my point, and then I can talk about the angle between, in our convention, between the positive x-axis in the counterclockwise direction. Okay, so thinking about how can I now write the coordinates of this point in our rectangular system, I will need to drop a perpendicular to the x-axis and think about the x and y components here, right? So normally I would describe the coordinates of this point as x, y, but I also have this angle that's present here that would nice to get in to be involved into these calculations. So this is where the definition of sine and cosine functions come from. On a unit circle, sine and cosine are simply x and y coordinates of this point. So the x coordinate is the cosine of the corresponding angle, and the y coordinate is the sine of the corresponding angle. So they're simply coordinates of that point on the unit circle. So let's write that down. X coordinate is the cosine of the corresponding angle, and the y coordinate is the sine of the corresponding angle. Okay? Originally, so maybe actually let me label this here too. So cosine will be the x coordinate, which means the length of this piece, and sine is the y coordinate, which means the vertical component here. Originally, when Greeks actually studied the angles, they studied double angles, so their pictures looked slightly different. And let me draw a picture the way they had it to emphasize where the origins of the names come from. So the pictures that they would draw would be like this. They would study not just the coordinates, but they really liked the symmetry, so they wanted everything to be symmetric in the picture. The name for sine in Greek means the bent one. Think about the signs on your face, right? The sinuses on your face. This is the same shape. So it's the bent one, or the bay, which approximates this vertical component here. Cosine, co means the other one, so it's the one that is related to sine. But even within the triangle, we have some words that we don't always understand the meaning of in English, right? This right angle triangle here, the length of this side, or rather this side, is called the hypotenuse. Hypotenuse in Greek means the stretched out one. And it's easy to see why you would call it the stretched out one, because if you look closely, this resembles a bow, right? And so if you actually try to shoot this arrow, you will stretch out along this side. Right, so the names have really nice origins, same with tangent and cotangent and secant, and we will talk about those later still. What the unit circle gives us is a whole bunch of information about sine and cosine right away, because this is actually where they come from. So for example, because it's a unit circle and its radius is 1, if cosine and sine are the x and y coordinates on the circle, we can see right away that they have to be between 0 and 1. They cannot escape the circle, which means that the both x and y coordinates have to be between -1 and 1 on the x-axis or on the y-axis here, which means both that sine and cosine have to be between -1 and 1. And this is where one of the first properties of sine and cosine functions come from. The next one that's useful too is, if you remember, what is the equation of a circle centered at 0 with radius 1? It's going to be x squared plus y squared equals 1. Now we know that the x-coordinate is cosine, so I can replace it with cosine. And we know that the y-coordinate is the sine, so I can replace it with sine. So altogether, I get cosine squared plus sine squared equals 1, or what is also known as the basic trigonometric identity, that is simply given to us by the equation of a circle on which this point moves. The next thing to think about here, in terms of where sine and cosine properties come from, are also their signs. So for example, let's think about cosine. Cosine is the x-coordinate of the point. If my point is in the first quadrant here, the x-coordinates of all of these points are always positive. And the x-coordinate corresponds to the cosine of the angle, which means that in this quadrant, cosine of the angle is always positive. Same with sine. Again, think about of all the points in this quadrant, sine is the y-coordinate. All the y-coordinates of these points are positive, which means that the sine of all the angles in this quadrant is also positive. Applying the same logic to the other quadrants, so let's take a look at these points right here. The x-coordinates of them are negative because they're to the left of the origin, which means that cosine, which is the x-coordinate, will be negative. But the y-coordinates of all of these points are still positive, which means that the sine will still be positive. In the third quadrant here, all the x-coordinates are negative and all the y-coordinates are negative, so both cosine and sine will be negative. As opposed to the fourth quadrant, the last one, the x-coordinates are positive, so cosine is positive, but the y-coordinates are still negative, so the sine is still negative. So this is where the beginning of your, whatever it is, all students take calculus, or whichever way you choose to memorize it, actually comes from. We'll talk about the signs of tangent and other trigonometric functions shortly. What unit circle also gives us is a really easy way to immediately evaluate some values for cosine and sine functions. So let's go through a bunch of examples here. Cosine of 0. So let's determine the point that this angle corresponds to. It's right here, right? This point right here. Cosine is the x-coordinate. What is the x-coordinate of this point? It's a unit circle, so remember that the radius is 1. So the x-coordinate of this point is going to be 1. Next question, sine of 0. So again, 0 is the angle that corresponds to this point. Sine is the y-coordinate. What is the y-coordinate of this point? It's 0. See, no need to pull out a calculator. Once you get used to doing these calculations from the circle, it's actually going to be faster than using a calculator to do that. Cosine of pi over 2. So let's think about what angle does that correspond to. Pi over 2 is 90 degrees, so up here. Cosine is the x-coordinate of this point. What is the x-coordinate of that point? It's 0. Next up is cosine of pi. Pi is this angle down here from the positive x-axis going all the way out is to pi here. Cosine is the x-coordinate. What's the x-coordinate here? It's to the left of the origin, so it's -1. Okay, proceeding in the same manner for the other angles. 3 pi over 2. So again, remember this is, it's easier to think about like it's 3 of pi over 2's. So 1 pi over 2, 2 pi over 2, 3 pi over 2. So we're at this point right here. We're asked about the cosine, so the x-coordinate. The x-coordinate of this point is 0. Cosine of 7 pi. So again, let's count off pi's. 1 pi, 2 pi. Now remember that the full circle is 2 pi, so we can also count in 2 pi's. So this whole rotation is going to be 2 pi. One more rotation is going to bring us to 4 pi. One more rotation is going to bring us to 6 pi, and then 7 pi will land us on this point on the circle once again. And so we're asked about the cosine, which is the x-coordinate, which is -1. And so we're beginning to see that some angles, due to rotation or otherwise, will have the same values for sine or cosine. Let's talk about the negative angles. -5 pi by 2. So it's -5 of pi by 2's. Okay, so starting from here, it's negative, which means we're going to be moving clockwise. So 1 pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2. So it's this point right here. And it's the sine, which means the y-coordinate of it, which is, of course, -1. This next one here involves an actual rotation. So notice what this is. It's 2k pi. So it's 2 pi k times. So that means that I'm allowed to go around the circle, which is 2 pi k times. So as many times as I wish. Okay, and this is true for any number k. So this signifies any number of rotations. Now, of course, a full rotation will not change the value of sine or cosine, because if I have a certain point, going full rotation will land me at the exact same point, not changing its x and y coordinates, which is why sine and cosine have this property that adding or subtracting 2 pi, no matter how many times, will not change the values of sine and cosine of that certain angle. So let's see what we have here. Sine of pi by 2 plus a rotation. So I'm at pi by 2, which is this point here. And again, no matter how many times I rotate in any direction, I will still be at this point here if it's a full rotation, which means its x and y coordinates will not change. So the sine and cosine value will be the same. I'm asked for the sine value of this angle. So the y coordinate, which in this case is 1. Remembering the definitions of sine and cosine functions from the unit circle will be useful in more ways than you can imagine. Let's take a look at some questions about the properties of sine and cosine functions. So first of all, we're asked, how many solutions are there to the equation sine theta equals 0.7? So remembering from the unit circle, let me pull up a quick sketch of that here, that sine corresponds to the y-coordinate. So this is essentially asking how many times on a unit circle is the y-coordinate equal to 0.7? Well, y-coordinate being 0.7, remembering it's a unit circle, so the full length of the radius is 1. 0.7 will occur, let's say, somewhere here. And of course, in the unit circle, we can see that this happened twice, on the positive side and on the negative side. So I can see that there's going to be two angles, in particular this angle right here and then this angle right here, that have that sine value as the solution. So the answer here is, how many solutions are there? There are 2 solutions on each revolution, right? So per rotation, 2 solutions between 0 and 2 pi. And then of course, with every revolution, I will acquire 2 more solutions. So it's also important to recognize, is the equation that you're looking at being asked for solutions for all angles or only for the one rotation? Next up, we're asked to evaluate sine of k pi, where k is an integer. So this is an integer, meaning that I am asked to calculate the sine value of any multiple of pi, positive or negative. So again, let's pull up our unit circle here, and let's think about what does that actually correspond to. So any multiple of pi, a whole multiple of pi. So it could be 0, so it could be here. So let me maybe mark this. So it could be this point here. It could be 1 pi, which is on this side. 2 pi will be here again, 3 pi will be here, and so on. And in the negatives, negative pi will bring us to here, negative 2 pi will land here. So I'm literally being asked about the sine value at these 2 points. Sine value, once again, is the y-coordinate. What are the y-coordinates of these 2 points? They're both, of course, 0. So sine of k pi is 0 for all values of k. Here, let's think for a second about what would be different if the question asked for cosine of k pi. So my points don't change. I'm still looking at these 2 points, but cosine is the x value, which means that I have to figure out what are the x coordinates of these 2 points. Okay, I can clearly see that the x coordinate of the point on the right is 1, and the x coordinate of the point on the left is -1, which means that the cosine will have 2 distinct values. It will be 1 if the rotation lands on this point right here, and -1 if it lands on the other one. I can see that we will land here for even values of k, so this will be 0, 2 pi, 4 pi, and so on. So it will be 1 for even k, and we will land on the other side for odd k's, like 1 or 3, and so on. So it will be -1 for odd k values. Okay? Next up are various expressions that involve sine and cosine, and we're asked to determine whether these guys are true or not. Again, let's pull up our picture of a unit circle to think about what these mean. So first one is asking, cosine of negative theta, is it the same as cosine of theta? So let's sketch an angle theta on our graph right here. So let's say this one, doesn't matter where it lies. We will try to analyze this in general. If this is theta, then negative theta, of course, will be right here, the same angle, but in the negative direction. Okay, and so we're looking at 2 points, this one and this one. We're asked, are the cosine values the same? Cosine corresponds to the x value, so is it true that the x coordinate of this point the same as the x coordinate of this point? Well, certainly I can see that this is true because the angle is the same, so this, of course, will form an isosceles triangle. So this line will go directly there, and so the x coordinates are in fact the same. So this is true. The next question is asking something about the exact same angles, but now the sine values. So the sine of the angle is the y coordinate, and it's asking, are the y coordinates of these 2 points the same? Well, clearly that's not true, but we can see that there is a relationship between them, and in fact they're exactly the opposites of each other. Whatever this y coordinate is, this is the exact same y coordinate, but in the negative direction. So we can fix that expression by adding a negative to it. Let me move my circle a little bit. So this expression, restated correctly, will be sine of minus theta is actually minus sine of theta. And that will be true of any angle theta. This is what makes for names of sine and cosine functions, or this names one of the properties of them. Cosine function is known to be even, which means that it absorbs the negative sign. Think about kind of like -2 squared becomes 4. So the negative sign gets absorbed because you do something twice or even number of times. Whereas a sine function is said to be odd because it takes the minus and gives it back. So something like a cubic function. Because if you cube a negative number, you'll get the negative back, okay? Let's look at some periodic properties of sine and cosine functions. So this is asking, is it true that sine of theta plus pi is the same as sine of theta? Well, where is theta plus pi? If this is my theta, pi is what makes up a straight line. So theta plus pi would mean I'm extending this line and looking for the angle exactly opposite of that. So this point will correspond to the angle theta plus pi. Okay, this is theta, and this is pi. So this point corresponds to theta plus pi. So is this true that the sine of theta plus pi is the same as the sine of theta? Sine corresponds to the y coordinate. Is this true that they're the same? No, they're clearly not the same, but we can see that they actually have the same relationship as these two guys, right? The y coordinate of this point is exactly the same as the y coordinate of that point, but negative. So I can fix that by adding a minus in front of it. The next expression is the one that students always make small mistakes with. So let's go over this one carefully. Cosine of 2 theta, is it the same as 2 cosine of theta? So this is my angle theta. Let's draw the angle 2 theta. So 2 theta will fall somewhere here, let's say, right? So this guy is 2 theta, this is theta, and this is another theta here. And so we're looking at the 2 points that correspond to the angle theta and the angle 2 theta. We're asked about the value for the cosine, which means that we're looking at the x-coordinates of these 2 points. Do these 2 points have the same x-coordinates? Clearly they do not, and we can also see that there's no inherent symmetry the way that we had it with the angle theta and minus theta. This got shifted not quite to the same level, so this expression is not true at all. In fact, we will see later on, and hopefully you remember from your pre-calculus, that there are double angle identities that clearly specify that it's actually hard to expand double angles in this way, or in general. Next up, we're going to talk about special angles and special triangles. We've seen that on the previous page, that there are some angles that are simply more used than others. Angles like 30, 45, and 60 degrees. Let's start with angle of 45 degrees. It's the nicest one. It's exactly halfway in between each quadrant. So if I construct a little triangle here that corresponds to that angle, this will be 45, or pi by 4. This will also be pi by 4. And this is 1 because this is the length of the radius of the circle. And I can see that because both of these angles are the same, that means that this triangle is isosceles, which means that this side is equal to this side. So whatever coordinate this point has, its x-coordinate is equal to its y-coordinate. So I can say that this actually has coordinate xx, meaning that this really just lies on like a perfectly diagonal line, which also means that the length of this side is x, and the length of this side of this triangle is also x. Now, thinking of this triangle, I can see that I've managed to label all the side lengths, and therefore I can actually use Pythagoras' theorem, which says that the length of one side squared plus the length of the other side squared equals to the length of the hypotenuse squared. So in this case, I have x squared plus x squared equals 1 squared. X squared plus x squared, of course, is 2x squared. And so I can solve this entire thing for x. X squared is 1/2, which means that x is plus or minus square root of 1/2. Now I can see here that my x's lie in the first quadrant, which means that they are positive, which means that in this case I will take x to be a positive square root of 1/2. I can rewrite square root of 1/2 as 1 over root 2, or if I choose to rationalize the denominators, I will get root 2 over 2. So you will see this as being stated as one of these expressions. Just because they look different doesn't mean that they actually are, so be careful. So this gives way to our very first special triangle, and that is the 45-45 triangle. I better actually make it look like they're equal sides. Something like this. There we go. Okay, so let me label it this time with degrees as opposed to radians. I know that everybody's more comfortable with degrees, but in calculus we really do use radians way more often, so it's a good practice to get used to radians now. So let me label this with radians as well. Pi by 4, pi by 4. If the length of the hypotenuse is 1, as it was the radius of the unit circle, then the lengths of the sides are 1 over root 2 and 1 over root 2. So the x and the y coordinate of the point corresponding to this angle on the circle is the same, which means that the sine and cosine values are also the same. The second special triangle, I'm not going to derive from the circle, it's derived very similarly, is going to be the 30-60 triangle. So a triangle, it looks something like this. Actually, let me make it a little bit bigger. So the angles are going to be 60 degrees, or pi by 3, and 30 degrees, or pi by 6, pi by 3, and pi by 6 here. This is my right angle. Again, the hypotenuse is 1 because it would have been the radius of the circle, and the lengths of the sides are 1/2 and √3/2. That is also derived from the properties of the circle, of the triangles in the circle. Using these two special triangles and these different values of the lengths of the triangles as they fit in the unit circle, we can compute all kinds of things in terms of sine and cosine values of the corresponding various angles. So let's take a look here. Cosine of 3π/4. So again, that means you're counting 3π/4s. Π/4 is halfway through the quadrant, so 1, 2, and 3 of them will land you right in the middle of the second quadrant right here. So now we gotta think of how do we fit this special triangle into this point here. And I can see, of course, that if I just drop the perpendicular there, this is my special triangle where this is π/4 and this is π/4, which means that I can now match the lengths of the sides to this triangle here, which means that now I have the side, maybe let me make this bigger. Now this side is going to be 1, this side is going to be 1/√2, and this last side is also going to be 1/√2. I'm asked for cosine value at this angle. Cosine, of course, is the x-coordinate, so I'm asked for the x-coordinate of this point right here. I know that this length is 1/√2, but I'm on the left side of the origin, which means that the x value of this x-coordinate of this point is minus 1/√2. Okay, and this is what it is. So you have to be careful about special triangles because as positioned in different quadrants, they will produce different signs, plus or minus, that corresponds to the cosine or sine value of that angle. Moving along, let's take a look at the next one. So this one is 7π/4s. Again, counting off in π/4s is counting by eighths of a circle. So 1, 2, 3, 4, 5, 6, 7 will land you on this point right here. So halfway through the fourth quadrant right there. And again, positioning your triangle, we can see that I can position it this way, where this is π/4, this is π/4. And so this is 1, 1/√2, 1/√2. I'm asked for the sine value, which means the y-coordinate of this point. Y-coordinate is this length or this length right here, but I can see that it's on the negative side. So in this case, it's also going to be minus 1/√2. Similarly, we're going to have two cases for the use of the other triangle. So let's see here, minus π/6. So I have to go just 30 degrees down. It might be a little more, something like this. Okay, so this is minus π/6. And now I have to find how to place this special triangle into this picture here. So my π/6, or this angle, is this angle right here, which means that I kind of took this triangle, turned it around, and placed it here like this. Okay, so sometimes it takes a second to really visualize. This is my π/6, which means that my triangle here got flipped to look like that, where this side then is 1/2 and this side is √3/2. I'm asked for the cosine value, meaning the x value. The x value, or the x-coordinate, is of course the length along the x-axis, which is this value right here, and it's on the positive side, so we get √3/2. Similarly, for the last example here, 2π/3s, so I have π/3 twice. Okay, so π/3 is like counting 2/3, so this is π/3. And then 2 more of them will land me right here, on this point right here. All right, so this is my 2π/3. And again, now that means that I have to find this triangle and fit it into this space right here. And what I'm going to do is I'm going to drop the perpendicular here, and I can clearly see my triangle forming. It's just this triangle, but sort of flipped and standing on its one edge, and now you have to label the sides correspondingly. So I can see that this side is going to be 1/2 and this side is going to be √3/2. The side opposite of the smaller angle is smaller, which is 1/2. The side opposite of a larger angle, which is 60 degrees, is bigger, or √3/2. Okay, so this is it. I'm asked for the sine, which is the y coordinate of the point. So this point right here, I can see that this is my value right here, and it's of course on the positive side of the y-axis, of the x-axis, so the positive y value. So it's also going to be √3/2. So how do we take this movement of the point along or on the unit circle and make it into a graph on the x and y axis? A couple of things to remember from before. Again, if we have a point that moves along, it's important to remember that the x-coordinate of the point is the cosine of the angle, and the y-coordinate of that point is the sine of the angle. Now, this is exactly where the definitions of the trig functions come from. With them come properties such as both sine and cosine are in between -1 and 1, which means that on my graphs, I don't have to go above -1 and 1 because my entire graph should be contained in that range. The other thing that's useful to analyze is the fact that I know that between 0 and pi, for example, the y-coordinate, which is the sine, will be positive. So between 0 and pi, my graph has to lie fully above the x-axis, and then between pi and 2 pi, it's going to be negative here. So at that point, it has to fully lie below the x-axis. And finally, it's important to remember that on every rotation, everything is going to repeat. This is what makes these functions what we call periodic. They repeat after a certain number of time. In this case, we know that sine and cosine functions repeat with a period of 2 pi. So every 2 pi, the picture or the motion of the point will be the same. So let's start with the graph of sine of theta. Again, recall that sine is the y-coordinate, so we will just try to put some points on the graph to see how it actually looks. At 0, we're looking at this point. The y-coordinate here of this point is of course 0, which means that on my graph that will correspond to the point 0 here. Notice that I've labeled the x-axis in angles just to be easier, so it's easier to graph the points. The next nice angle is pi/2, so this point right here, the y-coordinate of this point is 1, which means that at pi/2, the sine graph has to be up at 1. Next nice point on the quadrants is pi, and the y-coordinate here is again 0. The next quadrant point is 3 pi/2. Over here, the y-coordinate of this point is -1. And then at 2 pi, which is here, we're back at 0. So the situation from this point on will repeat itself. Now, I'm not going to plot any more points, but you can see how the function has to be nice and smooth because I am graphing y-coordinates of these points. So I'm graphing how high these points are on every single angle, right? So I know that this graph is going to be nice and smooth, and if I connect these points in a nice and smooth manner, I will get a familiar sine curve that will once again repeat before and after these angles. For the cosine function, I'm going to apply the exact same logic, but now of course I have to trace the x-coordinates of the point. So I'm going to start once again at 0, which is the angle that corresponds to this point here. The x-coordinate here is 1, so my graph here will start at 1. The next quadrant angle is pi/2. The x-coordinate here is 0, so at pi/2 I'm down at 0. At pi I'm at -1, so down here at 3 pi/2 I'll be at 0, and at 2 pi I will be back at 1 because I'll be back at the full rotation of the circle. Once again, I'm now looking at the x-coordinates of these points. So there are a couple of things I can notice. First of all, between 0 and pi by 2, the x-coordinates are positive, which means my graph will be above the x-axis here. Next region, between pi by 2 and pi, the x-coordinates of these points are negative, which means my graph has to lie here. And then I can apply the same logic to C, that I can simply connect the graph in a smooth manner to get a familiar portion of the cosine curve. And again, this is going to repeat, so I'm going to continue off with on the other two sides. Let's see a quick animation of this on Desmos. So this is my unit circle, and we're first going to witness how sine gets sketched. So as the point on the circle moves along, watch what happens to the height of the point. Okay, let me maybe zoom it out a little so we see more than one period. And let's go. See, as the height grows, it reaches 1, and then it starts going down, and then it becomes negative, reaches the maximum of -1, goes back up to 0, through back all the way to 1, and goes for one rotation after the next. Okay. These are the basic graphs of the sine and cosine functions. We can also apply all types of transformations the way we have before to these functions as well. So this is the most general form written here. Remember what these things correspond to. The constant being added to the outside corresponds to the vertical shift. The constant that is being multiplied by the function corresponds to the vertical stretch, or in this case, it's what's called an amplitude. Notice that the graphs here were stuck between -1 and 1 because the point was stuck traveling on a circle. But if I make the circle bigger, the radius of it being bigger, then my graph will have the bigger x and y coordinates that can actually travel in between. So this is what we will call the amplitude, the actual difference in the heights of the highest high and the lowest low. The C and the D here will both correspond to horizontal transformations. The one that gets multiplied is the horizontal stretch or compression. I'm going to call it stretch. And this D inside being added corresponds to the horizontal shift. Okay, so it's important to remember that the transformed function will not necessarily lie between -1 and 1. It will really depend on the amplitude and the vertical shift and so on. One other thing to trace is the period. We know that the period of sine and cosine is 2 pi, because that is the smallest distance before the function repeats itself. But due to the horizontal stretch or compression here, this period will change because the function will be either stretched or compressed horizontally. So for the transformed function, the period will also be different. So period for the transformed function in the general form is actually going to be 2 pi divided by this value of c. Okay, and just before we start sketching these functions on our own, take a look at how this works out on Desmos. So this is our familiar graph of sine of x, and on the left you can see here that I have the exact same transformations as we've seen on the previous page. So a, which is the vertical shift, will correspond to taking my function and just raising it up or down. B, which is the vertical stretch or the amplitude, if I take it to be bigger than 1, will simply stretch my function to be taller. Notice how the x-intercepts do not change throughout this entire transformation. And if I take to be smaller than 1, then it will flatten the function out. So wherever I decide to stay, let's say I've stretched it out a little bit, here it is. C will correspond to the horizontal stretch or compression. So if I take this function, notice that I will stretch it if C is bigger than 1, or if it's less than 1, it will expand the function out. So get it tighter and have a very, very small period where the function repeats more often, or have a much wider period. And then D, let me bring this up here, D will correspond to the horizontal shift left or right. So the function will simply travel to the left or it will travel to the right, depending on whether d is positive or negative. This is also sometimes called a phase shift. So we will always start with the basic graph of sine of x and then apply these various transformations. The first one we're asked to do is 3 sine of x. So this 3 outside corresponds to the vertical stretch, and therefore we will simply take the function and stretch it out vertically. Now here my graphs are all on the same scale. So one way to cheat the system is to change the given scale. So if my function now has to go from excuse me, -3 to 3, then my graph will be the same as the graph of the sine that I'm used to seeing. You only have to draw one period before you can talk about how it repeats. If I were to sketch the graph of the original sine, then it will be a more flat version of this. So my graph here is sine of x, and then my purple graph here is 3 sine of x. So notice that the x-intercepts did not change, it simply grew taller. If the 3 is multiplied on the inside, that corresponds to the horizontal stretch or compression. If the number is bigger than 3, then it's the compression. And this is also what affects the period. So in this case, my period is going to be 2 pi divided by the multiple, which is 3, so 2 pi by 3. That means that on the region from 0 to 2 pi, I have to see my function go through its full period 3 times. So let's draw the original sine function. Here it is. And again, it will repeat itself after the period. And now I have to be able to squeeze the same wave into this 0 to 2 pi, but 3 times. So where does that happen? Now that means that I have to divide the region from 0 to 2 pi into 3s. So I'm going to have a point somewhere here and somewhere here. I can see that these are approximately 3 equal pieces, and that means that my graph has to fully make an entire wave to be repeated in between these turns. So let's see if I can fit that in. My wave will look something like this. This is one period of it. This will be the second period of it, and this will be the third period of it. Now, of course, it's just a sketch, so my function is not perfectly symmetric or anything like that, but this is a good idea of how to actually have it transform. So my purple in this case is sine x, and my blue is sine 3x. For the next function here, it's exactly the opposite. I have x divided by 3, which means that that corresponds to a horizontal stretch, and the period here is going to be 2 pi divided by the coefficient in front of x, which is 1/3, which means that the period now has to be 6 pi. So that means that my function will take a full turn, not on 0 to 2 pi, but on 0 to 6 pi. So once again, let's cheat a little and adjust the scale here. This is going to be 6 pi, this is going to be 3 pi. I don't need the middle points here, and then pi and 2 pi will be somewhere here. So that means that my original sine function made a full period up until here. So my original sine function will look something like this and then repeat itself, right? So this purple is sine x, whereas my new function has to take the full turn, but on 0 to 6 pi. So it's going to be stretched out vertically, okay? So it's going to look like this instead. So this is my sine of x over 3. All right, and then this one is now all fully loaded with all kinds of transformations. So notice the amplitude change here. So that's the vertical stretch of 2. Notice that there's a -1 on the outside, so we're going to have to move 1 unit down. And notice the horizontal shift of pi by 2. So let me write this down, and it's negative pi by 2, so I'm going to shift right by pi by 2. This is going to be a little inconvenient to sketch on the graph that I have, but let's give it a go. So if I adjust once again the scale to be -2 to 2, Notice that my amplitude has to be 2, so I know I have to be at least that much in the range, but then I'm also going to move my entire picture 1 down. So that really means that I'm going to have to be working on from 1 to -3. Okay, so my original sine function will lie between -1 and 1, so my original sine function will, look something like this. Okay, this is my original sine of x. And now my new function has to be shifted 1 down and pi by 2 to the right. So this point at the origin will now have transformed to this point here. And the entire wave also had to be stretched by a factor of 2. So I'm going to have to start at -3, and my highest point will have to be 1, so somewhere up here. Right, so my origin shifted to here. So I'm going to take my sine function through here. It will actually cross over in the same spot, and then we'll continue on to -3 and beyond. Okay, so there we go. This is going to be my 2 sine of x minus pi over 2 minus 1. So keep in mind the scale that you have to work with and also the transformations that are given, being careful to apply each one in the right order. Let's recall that sine and cosine come from the fact that the point on the circle has x and y coordinates, and those x and y coordinates will be represented by sine and cosine. So cosine of the angle theta is the corresponding x coordinate, while sine is the corresponding y coordinate. By extending this line further, we will see where the other functions come from. So I will extend it further this way, and I will also draw a vertical line tangent to the circle to cross this extension. Then tangent from Greek means the one that touches. So tangent is actually going to be the length of the side of this big triangle here. Secant from Greek means the one that crosses. So secant will be the line that crosses the circle or the length that corresponds to the side of the triangle. Now, what we have in this picture are two triangles, this little guy and this big one. And they're clearly similar. They share all of the common angles. So by the similar triangles, we can derive a relationship between their sides. So here, let's think about vertical sides to horizontal side relationship. So vertical to horizontal, and see what that means for both triangles. Okay, so vertical side in my small triangle is sine theta, horizontal side is cosine of theta. So in the small triangle, I have sine theta over cosine theta. In the large triangle, my vertical side is tangent, and my horizontal side corresponds to the radius of the circle, or 1. So here I have tangent of theta over 1. And here is where I can already see the definition of tangent. Over 1 does nothing, so tangent is simply equal to sine over cosine. Taking the corresponding ratios of the hypotenuse to the horizontal side, let's see what this will yield. So in my small triangle, the hypotenuse is 1 because it's the radius of the circle, and the horizontal side is cosine. So I have 1 over cosine of theta. And in my large circle, the hypotenuse is what we call secant, whereas the horizontal side is the radius of the triangle, of the circle, so 1. So secant theta over 1. Okay, and this is exactly where we get the definition, the defining property of the secant. So here are the other 4 important trigonometric functions. Tangent, which above we proved to be sine over cosine. We also have secant, which is from here equal to 1 over cosine. And then you can similarly define cotangent of theta, which is cosine theta over sine theta. And this also gives a nice relationship that tangent times cotangent is 1, because if you multiply these two fractions together, everything will cancel out and you will have 1 left. And the last one is cosecant, which is 1 over sine theta. Now, thinking back to the basic trigonometric identity, we can now think about what that means in terms of these newly defined functions. So I'm going to take my basic trigonometric identity and divide everything by cosine squared theta. What would this yield? So let's take a look. Dividing everything means I get to break up all of the common denominators. So I'm going to get sine squared over cosine squared of theta. Sine over cosine is tangent. If they're squared, this will give me tangent squared theta. Plus, then I have cosine squared over cosine squared, which is just 1, equals 2. And then I'm going to have 1 over cosine squared theta, which will be secant squared theta. So the basic trigonometric identity divided by cosine squared gives me this new identity that connects tangent and secant. But I didn't have to divide by cosine. I could have divided by sine. So let's see what this will give me. Sine squared theta plus cosine squared theta equals 1. If everything is divided by sine squared theta, then, again, going piece by piece, sine squared over sine squared is 1, plus cosine squared over sine squared of theta. Cosine over sine is cotangent. Everything is squared, so this will be cotangent squared. And on the right-hand side, I'm going to get 1 over sine squared, which will be cosecant squared theta. Okay, so these are the other two versions of the basic trigonometric identities that now connect two pairs of the other two trigonometric functions. The other properties that are useful to remember or to be able to derive even better are where what function is positive on the unit circle. So once again, we always are going back to the fact that sine is the y-coordinate of the point and cosine is the x-coordinate. So in the first quadrant, both x and y coordinates are positive, so sine theta will be positive and cosine theta will also be positive. If sine and cosine are positive, that immediately means the tangent will be positive, the cotangent will be positive, secant will be positive, and cosecant will be positive. So in fact, all 6 functions are positive in the first quadrant here. For the second quadrant, notice that the x-coordinate is negative, which means that cosine is negative, but the y-coordinate of these points is still positive, which means that sine of theta is still positive. Okay, so cosine is negative, sine is positive, which means that tangent will be negative because we will have a negative divided by a positive. Cotangent will also be negative because we have the exact opposite case. Cosine is involved here and is negative, which means that secant will also be negative, but cosecant involves sine, so this will be positive. So the only two positive functions are sine and cosecant are positive. Rather, only sine and cosecant are positive here out of those two functions. Okay, and so you can go through the other two quadrants to figure out that in the last one, in the third one, cosine is negative and sine is negative. And in the fourth one, sine, of course, being the y-coordinate, is still negative, and the cosine is positive, which will give us that in the third quadrant, tangent and cotangent are positive. And, pardon, in the last quadrant, only secant and cosine are positive. So kind of the exact opposite situation to the second quadrant. Cosine and secant are positive. I strongly advocate for not memorizing this information, not only because chances are you'll memorize something wrong because there's quite a bit of information there, but also because it's just so easy to derive, it's not worth the hassle. So just remember, cosine is the x-coordinate of the point, sine is the y-coordinate, and then you can derive all the positive and negative signs for all of your main 6 trigonometric functions just from that one definition. What these definitions give us are also a way to actually compute specific values for certain angles and for all of the trigonometric functions. So here the question says that theta is an angle in fourth quadrant, which means this quadrant right here, such that the cosine of theta is 2/5, whereas to find the values of sine, tangent, and secant. Okay, so let's approximately sketch this actual angle. So if it's 2/5, I have to divide my 1 into 5, and then 2/5 will be this guy right here. It is the cosine, so I'm looking for the x value of 2/5. So my angle theta is somewhere in here. Right there. Perfect. So what I know is I'm trying to find sine, tan, and secant of this angle. What I do know is that sine squared theta plus cosine squared theta is equal to 1 for all the angles, which means I can solve this for sine, knowing the actual value for cosine. So from here, sine theta is plus or minus square root of 1 minus cosine squared theta. Okay, so always remember that when you are taking square roots, you have to get the positive and the negative. However, I know that this angle lies in the fourth quadrant. Sine will be its y-coordinate, so it will correspond to the negative value here. Okay, so make a note here. Since theta is in fourth quadrant, sine value is negative. Okay, so that gives me that the sine of my theta is negative square root of 1 minus cosine squared of theta. And I am given that cosine theta is 2/5, so I can just plug that value in. So 2/5 squared. And if we open up the brackets and simplify it a little bit, we're going to get minus root of 21 over 5. If you need some review of how to simplify various expressions like this, please take a look at Module 1 of this Precalculus Refresher course. So we found sine. Next up is tangent. Tangent, from the definition, is sine theta over cosine theta. And I already know both of these values. So sine is minus root 21 over 5, and cosine was given as 2/5. Okay, putting these two together, to divide is to flip and multiply. The 5s will cancel, so I'm going to get root of 21 over 2. And then finally, secant of theta is, of course, 1 over cosine theta, which will then give me 1 over 2/5 or 5/2. Okay? And we can also check that the signs make sense, right? Here, tangent is negative, and that is consistent with the angle being in the fourth quadrant. Secant is positive, and that is also consistent with the angle being in the fourth quadrant. Knowing the relationships between all of these trigonometric functions, of course, also allows us to both compute tangent, cotangent, secant, and cosecant at various angles, as well as to simplify various expressions. So let's start with computing some angles. Tangent of 5 pi by 4. So once again, this is 5 of pi by 4s. Pi by 4s are perfectly in the middle of each quadrant, so 5 of them, 1, 2, 3, 4, 5, will land me exactly here. Exactly halfway down my third quadrant here. So this guy corresponds to the angle of 5 pi by 4. Tangent, of course, is sine of 5 pi by 4 over cosine of 5 pi by 4. And I can remember that this corresponds to the special triangle of 45, 45, or pi by 4s and 90 degrees, where sine values are equal to cosine values. Now I can also see that in this quadrant, the x and the y coordinates of the point that the angle corresponds to will be negative. Both of them will be negative, which means that sine will be negative and cosine will be negative, which means that altogether, being equal values and the same sign, they will cancel out to be 1. For things like, for example, secant, remember that secant is 1 over cosine of pi by 6 in this case, and pi by 6 is simply in the first quadrant. It's a special angle in the first quadrant. Cosine of pi by 6 is root 3 over 2, so 1 over that will give me 2 over root 3. Excellent. And then if we're looking at simplifying expressions, the easiest thing to do is to bring everything down to be in terms of sine and cosine. So here I can expand tangent to be sine over cosine. And then, so this is what used to be tangent, and then times the cosine of theta. I can, of course, then see that cosines will cancel, and the entire expression can be simplified to be just sine of theta. Similarly here, I have secant and tangent, but they can both be expressed in terms of sine and cosine. So I'm going to do just that in hopes that it will actually simplify. So secant is 1 over cosine x, and tangent of x, so I have to divide by tangent, which is sine of x over cosine of x. To divide is to flip and multiply. So 1 over cos x times cos x over sine x. I can see that my cosines will cancel, and I have 1 over sine x, which I can leave as is, or I can also note that this is actually cosecant of x. And then in terms of computing angles, so similarly to this question here, if I am giving another function of the angle, I can once again think in terms of the functions that are basic ones, sine and cosine, that define it. So here I'm given that the secant of the angle theta is minus 3. So I have that secant of theta is negative 3. And I'm asked, what is the secant of minus theta? So secant of minus theta is what's in question. Secant of any angle is just 1 over the cosine of that angle. Now I know that cosine, we've discussed this earlier, is an even function. And again, recall that that's because if I have an angle theta, for example here, the angle of minus theta will be exact opposite of it here, but cosine corresponds to the x-coordinate of those 2 points, which are going to be the same. So cosine of minus theta is the same as cosine of theta, but 1 over cosine of theta is just secant of theta, which I know to be minus 3. Okay, so by taking secant and going through the definition of cosine, which we can analyze a lot better, I'm able to derive that expression. Moving on to think about graphs of these other trigonometric functions, let's once again recall the definition, starting with tangent. That tangent of theta is simply sine of theta over cosine of theta. So one thing that comes to our attention immediately is the fact that this function has a denominator, which means that I am looking for issues when the denominator is here equal to 0. So when is cosine equal to 0? Well, recalling our very handy unit circle, let's remember that cosine is the x value of the corresponding points. So when are the x values 0? Well, at this point up here, which is pi by 2, at this point down here, which is 3 pi by 2, and then once again every other pi. So pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on. So this will be a problem for theta being pi by 2 times some number k, where k is odd integer. Okay, so every other pi, because for the even integers, it will fall on here, because it's going to be 2 pi by 2, and we don't have that issue there. Okay, so with this in mind, that means that at those points, I'm going to have the function be undefined, which will be represented by vertical asymptotes. So at pi by 2, I'm going to have a vertical asymptote for the tangent, at 3 pi by 2, and at every other pi by 2. Now, the other thing to analyze is to maybe put some points on the graph. So for example, let's compute tangent of 0. Tangent of 0 is sine of 0 over cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so this is not a problem, it's 0. So we have tangent being 0 here. If we do the same calculations for pi, we'll discover that it's a 0 there as well, at minus pi, and so on. So in some sense, we have zeros alternating with asymptotes every pi by 2. The other thing to maybe think about is when is this function positive and when is it negative? From the previous page, we know that it's going to be positive in the first quadrant and in the third quadrant, and be negative in the second and third. So that means that the tangent function between 0 and pi by 2 has to be above the x-axis, But in the next quadrant between pi by 2 and pi has to be below the x-axis, above and below, above and below every pi by 2. So we can already see a periodic shape forming every pi, and that is in case the fact that the period of tangent function is pi. The other thing to watch out for, of course, is the domain. As we've already claimed, x cannot be pi by 2 times k, where k is odd integer. And so with a little more plugging in of various points, which I'm going to skip, you should get the graph of tangent that looks like this and repeats itself every pi. Once we have the graph of the basic tangent function, we can of course talk about transformations and variations the ways that we have before. And in this case, this form is very similar to the sine form, and it's going to represent the exact same things in terms of various constants. So this a will correspond to the vertical shift. This b will correspond to the vertical stretch. But notice that we cannot talk in this case about an amplitude because the graph does go off to positive and negative infinity and is not bounded by the two values. So this is not an amplitude, this is just a vertical stretch. Whereas this d will correspond to a horizontal or phase shift, and this c will correspond to a horizontal stretch or compression. And so the only other thing to think about in terms of the general functions are the same types of things like period and the domain. So the period, as in the sine case, will be affected by the horizontal stretch or compression. So in the case of these general functions, the period is going to be pi, which is the period of tangent, divided by c. And the domain will really depend on what the rest of the transformations do. So the domain here does not include these asymptotes, but these asymptotes will shift with the entire function, right? So if there is a horizontal phase shift, they will shift left or right. So the domain will really depend on how the shift happens. And I leave it up to you to decide what is that going to be in every particular case for a particular transformations. The graph of the cotangent will be very similar to this one, and I encourage you to look it up or develop this on your own from the definition of the cotangent. Let's take a look at the graph of secant, keeping in mind that cosecant will behave somewhat similarly or can be analyzed similarly. So secant, by definition, is 1 over cosine, which again, in the exact same way as for tangent, means that the denominator here cannot be 0, and when it is 0, we're going to have vertical asymptotes. So once again, that means that theta is pi by 2 times k, where k is odd integer. So in this case, I'm going to have the exact same asymptotes as I did for the tangent graph. But now notice that the secant only involves cosine. Tangent had sine over cosine. Here, it's a reciprocal of cosine. So maybe it's a good idea to start with the graph of cosine and then see what happens there. So the graph of cosine will go through these points. I usually like to draw a couple of points for the cosine just to make sure my curve looks decent. Okay, so there we go. And now it becomes clear, of course, that when cosine is 0, which is all of its x-intercepts, is exactly when 1 over cosine does not exist, which means that every x-intercept of cosine becomes a vertical asymptote of secant. It's also clear that at the points, for example, 1 and minus 1, the graph of secant will be in the exact same spot, because 1 divided by 1 is 1. Let's write that down. It's a very insightful observation. And 1 over minus 1 is just minus 1. So the points on the peaks and the valleys here are actually going to be shared between the two functions. And then the next observation is the fact that, again, I'm talking about a reciprocal function here. So if I divide by a very small number, 1 divided by a small number produces a large number. And the smaller the number that I'm dividing by, the larger the output. So as we start off here for the secant, as the cosine decreases, I am dividing by a smaller and smaller number, which means that my corresponding output for the exact same x values will produce larger and larger values as their reciprocal result. Okay, and so this is exactly how the graph will look like. Starting here, it will actually grow toward the vertical asymptote, and the same thing is going to happen on the negative side here. The exact same logic can be applied to the negative branches of the secant to see that this is what they look like. So let me just make sure that I label this graph correctly. This is secant, and this was cosine. Okay, as we notice, the graph repeats itself every pi, right? So this is not the case as with tangent. This graph does not repeat itself every pi. It repeats itself every 2 pi. So I will see this branch again over here as the cosine moves up. So the period of secant is 2 pi. Okay, and the asymptotes, or the domain, depending on how you prefer to list it, will be at pi over 2k, where k is odd integer. Okay, so the domain will be all of the values that do not include that. So let me state this in terms of the domain here. The domain will be all x's not equal to that, or all thetas, because my entire expressions above are in thetas. Okay. For the cosecant, you will go through the exact same logic, except you will start with the graph of the sine function, and therefore the cosecant will actually be the corresponding branches on the peaks and the valleys of the sine function. For the transformations, again, everything is exactly the same. The outside addition will correspond to vertical shift, the number that the multiple up in the front will correspond to vertical stretch. And again, here we cannot talk about the amplitude because the graph of secant does go off to positive and negative infinity. This will correspond to a horizontal stretch or compression, and this will correspond to a horizontal shift. And this, of course, then means that the period will be affected by the horizontal stretch or compression factor. So the period in this case will be 2 pi, which is the period of the secant in the basic form, divided by c, and the asymptotes and the domain will depend on the horizontal shift that occurred here. So you are probably going to find it easier to evaluate that for a particular transformation of the secant function. Please take a look at Webwork Assignment Module 6a. Trigonometry is one of the many things that requires a lot of practice to really get comfortable with, but you will reap huge benefits of that once you enter calculus. There's also a bunch more of exercises that follow this section that allow you to work on your understanding of the definitions of the basic trigonometric functions, so I encourage you to do those as well.